Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today on Foundational Mathematics, we want to talk about vector calculus, in which we will be talking about calculus, but instead of doing it with scalar parameters, we'll be using vector parameters. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. So so when we go to vector calculus, here are here are the topics that I'll be discussing throughout this entire video. So the first we'll be talking the about vector analysis. So we'll be introducing back vector analysis. So maybe if you have already forgotten about how vectors work, in here I'll be reviewing everything that you need for you to do vector calculus. After that, we'll be talking about the time derivatives of vectors. And then we'll be differentiating between scalar and vector fields. And then after that, we'll be talking about multiple different types of integrals, something like the line integral as well as the surface integral. And so later, after that, we'll be later talking about the scalar field, and then it will have a relation with something which you call as the gradient. And then also for vector fields, you would have something which you call as the curl, as well as a divergence. And then these three things could be encapsulated into one as something which you call as the differential operator. And then finally, we will be discussing about higher derivatives. And then after that, we'll be talking a little bit about the applications, and specifically applications for electromagnetism. So there will be some physics throughout this discussion. So if you want to skip through the videos, you could check the timestamps here for you to skip through the video. So let's go and first talk about how do you do vector analysis. So what a vector is. Vectors are just objects which has objects with magnitude and direction. So something that is very familiar when you're talking about vectors is an arrow. And so an arrow is pretty much something which you call as a vector. And this vector could be multi-dimensional. It could be 5-dimensional. So it would have 5 different parameters, and it has its width as well as its direction. So this is what we call as a vector. And then the way that you add vectors together is by simply just joining them together. So if this is A, this is B, this is A plus B. So you could just move it around. So as long as you don't change the direction or the magnitude, a vector is still the same vector. So this is how you do addition. And then if you want to do multiplication, it is simply just by adding things up or scaling things down. Pretty much you're just changing the magnitude. So if this is A, this will be 2A. And the magnitude, which is normally denoted as the absolute value of A, is something written like this. So if you have 2A, it is pretty much just 2 times the magnitude of A. So after that, we could also talk about the null vector. So the null vector is pretty much a vector in which its magnitude is 0. That's just the idea. Another thing for you to note down is that you could have something which you call as unit vectors. So unit vectors are vectors which magnitude is 1. So something like I has a magnitude of 1. And these unit vectors could form a basis, or something which you call as an orthonormal basis, in which both bases must be normal to each other. Something like this and this. If this is I, this is J, this is perpendicular to each other, this is something which you call as a orthonormal basis. And using only orthonormal basis, you could construct almost every different type of vectors. So if you have a vector A, you could write it in terms of multiples of I hat plus multiples of j hat. And this is the way that we normally denote this. So this is just a pretty much a introduction of vectors, but maybe you might be asking, what about if I change the basis by a certain degree? So maybe if I do it something like this, so I add an additional angle called theta. And the question is, what will be the vector, let's say the same vector A, in terms of these coordinate systems? So we could start to think about this much more thoroughly. So we could actually express our new I hats in terms of, no, sorry, so let's say this is I hat bar, no, sorry, I hat prime, and this is I hat. So this is j hat and j hat prime. And so we want to figure out what I hat prime is. So if we try to solve this, I hat prime will be, so if we think about this, there is a component within this direction, so that will be like the cosine of theta in the I hat direction, and then you would have the j hat component, so plus sine theta j hat. And so you could also do the same thing for j hat prime. It's gonna be, so from here it's negative sine theta I hat plus cosine theta j hat. And so with this coordinate system, you could just construct a vector to be a prime, no, sorry, yeah, a prime x in the I hat prime plus ay prime in the j hat prime. And so with this, you could actually try to solve what is a prime x. The easier way for you to actually to convert from one point to another is by doing the reverse. So technically this is correct, but we could also express this of I hat and j hat. So you could also just re-express everything back. So if you just pretty much do the system of equation, you could still get the same result. It's gonna be, so the I hat is gonna be the cosine theta of the I hat prime minus sine theta of the j hat prime, and then this one is sine theta I hat prime plus cosine theta j hat prime. So you could just substitute this guys into your a vector in the basis of I hat and j hat. And so what you would get is that this a prime x is gonna be, so you could just do it by term addition, because it works like algebra. So it's ax cosine theta plus ay sine theta. And so this is for ax prime, but for ay prime, it's gonna be negative ax sine theta plus ay cosine theta. So this is just a way for you to convert from one system to another when it comes to rotational transformation. So in here we only discuss about 2 dimensions, but what about if we talk about 3 dimensions? How do we denote the basis? And so there are different ways for you to draw the basis. You could have I hat and j hat here, and then the k hat would go towards out of the screen, or you could make it inside the screen. But in here, we'll be using the right hand rule. So if you take your right hand and then you form, so if this is your index finger and this is your middle finger, and so if this is your right hand, you would later have, oh sorry, I think I have too much fingers there. You would have your thumb to be pointing out of the screen. And this is what you call as the right hand rule. So if this is your I hat, this is j hat, this direction will be your k hat. So this is the one that we don't use. So we'll be using this notation throughout the video. So after we have discussed about addition as well as multiplication with a scalar value, we want to talk about multiplication, but instead of multiplying it with a scalar vector, a scalar value, we'll be multiplying it with another vector, and we'll see what it means. So in terms of multiplication, we have two different types of multiplications. One of them is the dot product, and the other one is the cross product. So what's the difference? So for a dot product, the dot product is a way for you to write something like this. If you have two vectors, A and B, and then you take the dot product of it, you pretty much try to find the magnitude when B is projected on A, and then you just multiply the length. That's the definition of a dot product. So A dot B is just the length of A, multiply that by the length of B while it is projected. So if this has an angle theta, it would mean that it will be B hat cosine theta. And this is the definition of a dot product. So something interesting about the dot product is that it is distributive. So if you have A plus B, A1 and A2, everything dot product that with B, it's the same thing as A1B plus A2B. So first it's distributive, and second of all, it is commutative. A times B is the same thing as B times A. So with that information, we could actually extend our understanding of the dot product much more further. So let's say if we are dealing with three-dimensional vectors, axi hat, ay j hat, plus azk hat, and then you dot product this with bxi hat plus byj hat plus bzk hat, what will be the cross product be? And so we could actually figure this out, because first of all, it's distributive. This means that we should just do every single combination of the multiplication. Same thing as multiplying x plus y times x minus y. But in here is something that we need to note. axi hat dot bx dot I hat, this is something, right? But if you know from the properties of the magnitude, you could just extend out your magnitude. So if we say that axi hat dot, so what's axi hat plus bxi hat, let's say, it's going to be the same thing as taking the magnitude of ax dot the magnitude of bx I hat technically, but the lengths are ax and bx, and the I hat, its angle is always 0 degrees, so this is multiplied that by 1. So it's always just the ax times the bx, or pretty much the way that you could extend this is that I hat dot I hat is always 1. And same thing for j and k, and for any other vectors. If they have the same direction, you just need to multiply the magnitude. But if you are taking, let's say, ax I hat times by j hat, I hat dot j hat will have an angle of 90 degrees, or this will result to 0. So for any other values which are not the same, which doesn't have the same direction for the basis, its result is 0. And this is a property of the dot product, is that if you take the dot product of two different vectors, you could figure out the angle straight away, thanks if you know about the dot product as well as the magnitudes. And then if you know the ratio, you can figure out what the cosine theta, which means you figure out what the theta is. So it's a very useful information for you to know what does the meaning of a dot product truly means. So going back, after we have already developed this entire thing, we could state that the dot product is just ax bx plus ay by plus az bz. This is always true even for higher dimensions, because if you do the same method, it will always result into the same type of formula. So after we have talked about the dot product, we should now talk about the cross product. So what is the cross product now? The cross product is pretty much just a product which determines the area between two vectors. So if you extended something like this area is your magnitude of the cross product. And so the magnitude here could be defined as the magnitude of A, so it's base times height, but then the height, so if this is B, this is theta, the height here is sine theta times B, times the length of B. So it's A times B times the sine of theta. So that's the magnitude. But what about the direction? The direction could be defined by taking the right-hand law. So if A times B is like that, that means that it should go upwards. So it's the same thing as saying I hat cross j hat is k hat. So if you point your index finger in the I hat direction, your middle finger in the j hat direction, your k hat will be your thumb. That's the way for you to define a right-handed coordinate system. And so some properties of the cross product now is, so first of all, A cross B really means the area, a vector in which the magnitude is the area, and then the direction is the one that is normal to the plane. That's pretty much just the definition. But also, what we could also gain from this is that A cross B is not the same thing as B cross A. Instead, it's the negative. You could express this just by taking your right hand rule, and then if you do it in the other direction, it will later flip your hand. So this is why A cross B is not the same as B cross A, but it's the negative. Another thing is that a cross product is also distributive, meaning that you could do the same thing as before. So what you could do now is that if you have A cross B here, so if we have AX I hat plus B AY J hat plus AZ K hat, and then you take the cross product with BX I hat plus BY J hat plus BZ K hat, what you would end up with is, so because this is distributive, you could just do it the same thing as x plus y and x minus y, same thing as the dot product anyways. But then you would figure out something out, that this relation is always true, but j hat cross k hat is always I hat, and k hat cross I hat is j hat, but I hat cross I hat is 0, and same thing for any other values in which its direction is the same. It makes sense because if you try to make a parallelogram in which it has the same direction for the vectors, you don't have a parallelogram. Instead, you would have a line. So this is why the result is 0. So if you express everything out, it will form into I hat of AYBZ minus BYAZ plus j hat of AZBX minus BZAX plus k hat of AXBY minus BXAY. So you could see that this is very tedious. And so later on, I will later introduce a method for you to... I will be introducing a method for you to determine the cross product from matrices, which I will do that on the next video. Lastly, what I want to talk about is the triple product. So the triple product is just pretty much multiplying the vector 3 times. And this is defined to be A dot B cross C. And the property of this is that you could actually just do it like this. B dot C cross A, and same thing as C dot A cross B. You could do it in a cyclic manner, but you couldn't do it the opposite way. And what this is that it is just the area of a parallelepiped, I think. So it's pretty much like a parallelogram, but instead it is within the third dimension. So if you could compute the cross product and the dot product, you could also determine what is the what's the volume of this three-dimensional object. So after we have talked about the general rule of doing vector analysis, I want to introduce the idea of the time derivatives. So time derivatives is pretty simple. So if you have a vector, let's say A, let's just use R vector, which has x of t in the I hat direction, plus y of t in the j hat direction, and z of t in the z direction, in the k direction. If you take the derivative with respect to time, what you would get is just the dx over dt of I hat plus dy over dt of the j hat plus the dz over dt of the k hat. It's just that simple. And so this is what we normally call as the velocity. And then if you do another derivative, it's something which we call as the acceleration. And this is very much related to the physics. You have position, you have velocity, and then you have acceleration. But maybe you could ask us, what about if we do a system in which its coordinate system is polar coordinates? So our vector is gonna be just r times r hat. So r hat is the direction of the position, and then the r is the distance from the origin. So it's something like this. You could have a vector pointing at something, and this direction is what you call as the r hat, with magnitude r. So we could try to determine what is the velocity. Well, we'll be thinking of this in 2 dimensions first. So if we are doing this, the r hat here, so if we take the derivative, this will be the d over dt of r dot r hat. Now here's the thing. Something that is fortunate about dot products and cross products is that they also follow the product rule of the derivatives. So if we try to think of this straight away, what you would get is that from the product rule, it's dr over dt dot the r hat plus the r dot the dr hat over dt. Now this is something that's very questionable. What is the dr hat over dt? And here's a way for you to solve this. R hat direction is already defined because if we know from previously, we figure out that if you change the direction, you could have something like this, right? And this thing here is very similar to the r hat. So what you would have here is the cosine theta in the I hat direction plus the sine theta in the j hat direction. And this turns out to be negative sine theta I hat plus cosine theta j hat d theta over dt when you take the dr hat over dt. Now, this negative sine theta I hat plus cosine theta j hat, if we actually take a reference back, it's the j hat prime. So this thing here is what we call as the theta hat. So it also follows the right hand rule pretty much. If you take your index finger straight away and then point your middle finger, it will be bending towards this direction. So it's always tangential to the r hat. And this is what we denote as the dr hat, which is the d theta dot the theta hat direction. So we can now convert this into dr over dt in the r hat direction plus the r d theta over dt in the theta hat direction. Now this is something that you are familiar with if you're doing physics. D theta over dt is omega, or the angular velocity. So r omega is your velocity as long as your r isn't changing, which does make sense. And so you can pretty much figure out almost every single type of kinematics as long as you know time derivatives when you're dealing with vector calculus. But that's just the velocity. What about the acceleration? So when you're doing the acceleration, you could do the same idea. You'll be doing lots of dot products, but the result will be d squared r over dt squared, the r hat direction. Add this by the dr over dt, and then the dr hat over dt, which turns out to be dot the d theta over dt in the theta hat direction, and then you add this again with r times omega times theta hat. So yes, it's gonna be so it's dr over dt times omega in the theta hat direction. You add this with another term, yeah, r times the d omega over dt in the theta hat direction, and then you add this again by another interesting fact. What is the d theta hat now? And so if you do the same type of intuitional crunch, what you would obtain is that the d theta hat is gonna be just the it's just the dr, no sorry, it's the d theta dot the r vector, the negative r vector. So this is another transformation again. So what you would get is the r times omega times the negative omega in the r hat direction. So if we compile everything in, what we would get is d squared r over dt squared minus r omega squared, everything in the r hat direction, and then you add this with, so this is omega. So it's 2 dr over dt omega plus r d omega over dt in the theta hat direction. Now, if your r doesn't change at all, what you observe here is that there are two different types of forces. This one, which is normally what you know as the centripetal force, centripetal, and this one, which is just r alpha, which is something you also obtained when you did circular motion. So you could see lots of elegant features when you dealt with vector calculus. So now I want to discuss about scalar fields as well as vector fields, since these two things are very important when we talk about physics. So scalar fields are pretty much fields in which it is filled with scalars. So something that you could actually think about this is that if you have like a map, and your map here has heights, let's say this part here has certain height, let's say 10, and here it's 20, and then etc. What you could state is that your height here is like a field. So it's like a height field. Well, it's a very weird thing to say, but it tells you that for every single point, it has a certain value, in which the value is dependent on your x and your y, and maybe sometimes even time. And this is the idea of fields. So you could have scalar fields in which your values corresponds to a scalar, something like temperature, height, pressure, and etc. But when you talk about vector fields, instead of having heights, let's say, you would have vectors. And so sometimes your vectors could curl, sometimes your vectors could diverge out. And this is where the idea of divergence and the curl comes in. And then later you could also express from the scalar field, you could get gradients, and everything will be related when we talk about the gradient, curl, as well as the divergence. So that's just the simple idea of differentiating between scalar fields as well as vector fields. So why do I discuss about these types of fields? And this is because that we'll later be discussing about line and surface integrals. So we'll just be talking about line integrals first. And the best introduction of this is work. Work is denoted to be F times S. well, the dot product of it. But remember that S is just the position vector, and then if you take a very small incremental dot the F, this will be corresponding to a very small work that you did. But if you actually take the integral of this will correspond to the addition of these small works. So if you have, like, let's say, if you are within a, let's say that there's like a force field going in this direction, and then you're taking this path, you could just take every small incremental steps and then just dot it with your force, and this will obtain your work. And then if you add it for all of these steps, you would get the total work. And this is what you call as the line integral. This is the idea in which that you take a very small incremental, you dot it with your actual force. So this is technically the S vector. So sometimes this type of notation is very hard for you to use, since you need to know all of the positions, all of the forces. So maybe instead of doing this type of handwriting, you could also denote it as F vector dot the dr vector over dt dot dt. And this is something that you might be familiar with. dr hat over dt is just the velocity, and then this is like the force over dt. So this is like the power over time. If you know your velocity, your change in position over the change of time, multiply that by your force, and then you have a parameter, let's say time, you would know what's the force. What's the work needed, or your line integral. And this is very similar when we talked about complex numbers. So at complex numbers, we introduced this type of integral, which we state that this is something which we call as a contour integral. And in line integrals, you also have contour integrals, because you could just loop around. You could just make a loop and do a line integral, and the result is not always 0 of FDR. So there are properties of this. If this is equal to 0, this is something which we call as a conservative field. So it's very similar to the idea when we talked about conservative fields, when we talk about analytic functions. Well, it turns out that almost every analytic functions are conservative. You could extend this idea for line integrals and state that certain force fields are conservative as long as the f.dr is 0 for any closed path, meaning that it only depends on your endpoints, not on the path that you're taking. Sorry, my bad. So this type of contour integral, my bad. So f vector dot dr vector could technically be 0 for an arbitrary path, but for any type of path, if the contour integral is 0, it's a conservative field. That's something that I want you to highlight. This is for every curve, every closed curve. So that's about line integrals. But what about surface integrals? So surface integrals, the easiest idea to think about this is flux, or maybe current. So, or pressure maybe. Well, there are lots of different ways for you to interpret this, but the surface integral pretty much states it's f vector dot dA vector. Sometimes we denote this as flux. And if you take this integral, what you would get is the flux. And so this is what we call as the surface integral. And so sometimes when we do this is pretty complicated. And so the way that we actually try to solve this is that we actually express the A vector in terms of other vectors. Maybe like dx, dy in the k hat direction, sometimes something like that. As long as you could parameterize your area, you could do the surface integral. And also another thing about surface integrals is that there's a way for you to denote which direction is your dA vector. So dA vector is, so you could just choose an arbitrary dA vector. But if you have a closed surface, it is conventional for you to write your dA vector outwards. So pretty much the flux really depends on your notation of going outside or inside. If you state inside is positive, your integral might be positive, but if it points outwards, it might be negative. So in this entire discussion, I want you to remember that for a surface integral, for a closed surface integral to be precise, every single vector points outwards. So let's first talk about the gradient. So the way that we define the gradient is by first thinking of the idea of, so for gradients, this is like the first derivative of a scalar function, of a scalar field. So we'll denote a scalar field to be phi. So d phi is normally denoted, so if you expand the differential, it would be d phi over dx dot dx plus d phi over dy times dy, and so on. And so with this, we could actually express a certain idea. We could call this as the gradient of phi dot the dr. So the dr is just the dx in the I hat direction, dy in the y direction, and so on. And the gradient of phi is defined to be the d phi over dx in the I hat direction, the d phi over dy in the j hat direction, and so on. And this is what we call as the gradient. So the gradient really pretty much tells you, so it's like the highest ascent. But normally when you talk about physics, we normally talk about the negative gradient. And this is because it's pretty much related to potential fields. So let's say if you have like a ball, and then you put it on this surface, on this scalar field phi, and then you put a ball and then see where it rolls. The way that it rolls corresponds to the gradient of phi. That's the way that you could actually interpret this physically. And so now, with this type of definition, we could extend the idea when we did at chapter 3 about Lagrange multipliers. The gradient of f must be equal to the lambda of the gradient of g. This gives a very subtle new meaning. Is that the highest descent in the f direction must be the same thing as the highest descent in the g direction. They both must have the same direction. And here's a very simple reason. If this is your boundary, and if you test every single point, if you want to find where it is the maximum or minimum, you need to go in the direction of the f, of df. So it couldn't be where it is parallel to each other. It couldn't be, because that means that you would still have a much more minimum value. So instead, you would actually just bring your path towards this point where it is normal to both the g as well as the f. And so if you know about these gradients, you would know where it is the minimum or where it is the maximum. This is a simple way for you to think about the Lagrange multiplier. Another thing about the gradient is that after we have developed this, we can just write the integral of d phi, right? Which is just phi 2 minus phi 1, or the one at point 2 subtracted by the point 1. It's just the change of this. And so we could extend this further just by taking the gradient phi dr, and it's always conservative. This is something very elegant. Is that if you know that your vector field is a gradient of a certain scalar function, you know that it's conservative. This is one of the ways for you to figure out if something is conservative or not, is by only doing this type of rule. So what I expressed here is mostly on Cartesian coordinates. But what about if we talk about in other types of coordinate systems? So I'll be doing a derivation of this. So the way that we'll do this is by just doing dr hat is the same thing as, so if we take the differential of the position vector, I want to state that I'm interested in one particular direction, dui, in the EI direction, it will have dr vector over dui, right? And then you could extend this further. And this is something which we'll denote as hi. So we'll have ei hi dui. That's the first thing that I'll be doing. So after that, we can now express what the d phi is straight away. Because, okay, so d phi is going to be the gradient of phi dot this sum of ei hi dui, right? And this must to correspond to, so the d phi here must to be the d phi over dui plus the d phi over the du2 and etc. Sorry, in the E1 direction. No, sorry, my bad. So, no, yeah. So this is the definition of the differential. So I want this thing to be the same thing as this guy, which comes from this guy. So now, we could use a very simple method, which is just matching it up. I just want to get a gradient in which this is correct. And a simple way to make this equals to this is just by multiplying it by the same vector, by the same basis vector, ei, so that the magnitude will be 1 straight away. And then you could just cancel out the hi's, this times the dui, du1, du2, and etc. Right? So you could just express ei over hi, and then you would have the du1 to be the same. This means that you would need to multiply this by the d phi over du1 or dui. And if you take the sum of this is just the gradient. So this is the definition of the gradient in other coordinate systems. It's a very, it's like a guessing game, but if you understand about this, you could just derive what is your gradient for an arbitrary type of coordinate system. So something that I want to discuss here is that this ei corresponds to the direction, dui corresponds to the small parameter within that direction, and then dr over dui is the scaling factor. And this is very important when we talk about the curl as well as the divergence. So let's talk about the curl. So what's the curl exactly? The curl. So the curl pretty much starts from the idea, if you take a contour integral f dot dr, and the question is, can I express this in another term? And this is very similar when we did the expression that it is conservative for a analytic function. So if we state that if we have a very small box here that we want to compute its contour integral counterclockwise, and we want to figure out what's the line integral. So we could do the same method. We could start 1, 2, 3, 4. Okay. So we could start going from the first path here, which goes from x to x plus dx. So this is x plus dx. So it has the width of dx, the height of dy. So if you take this of the fx dx direction, so this is x point y. So by the way, this dr here is just dx plus dy pretty much. Dx in the I hat direction and dy in the j hat direction. And so if we just only move it within the x direction, you don't change the y, which means that you don't have the j component. And this is true for all of the other terms, such from y to y plus dy, of the fy x plus dx point y times dy plus the x plus dx until x of fx x point y plus dy, yep, the x plus the integral of y plus dy until y of f y x point y dy. So if you try to take the integral of this entire thing, I will just denote it as big F of big X here, of x plus dx point y minus F big X of x plus, x point y. And then if you do it for all of the components, so we would have F big Y for this guy of x plus dx y plus dy minus F big Y of x plus dx point y, and then you add this with F big X of x point y plus dy, subtract this by F big X of x plus dx point y plus dy. Add this with Fy of x point y, subtract this by Fy of x point y plus dy. So this is the entire expression of the integral, let's say. So with this, we could actually observe certain phenomena. We could match this and this up, this and this, this and this, and this and this. So what we end up getting is the partial fx big X over partial y. Subtract this by the partial f of x in the, wait, it's in the same direction? Okay, sorry. So this is evaluated when this is x plus dx. No, sorry. When this is x, and then the same thing, but evaluate that at x plus dx. And then if you do the same thing for the other side, it's the partial f big Y over partial x. Yep. Evaluate it at y plus dy minus the partial f big Y over partial x at y. Now what we see here is that we also have another type of derivative here, which is going to correspond to the partial fx over partial y of partial over partial x negative, because the order is flipped, and in here it's the partial of partial fy big Y, and big X over partial x partial y. Well, it's partial y partial x, but you could later flip it because we'll just be assuming that the f's are continuous anyways. So what we could end up writing here is that if we swap this out, the partial fy over the partial y is just the fy, but small y, because it's now not the integral anymore. So it's the partial fy over partial x, subtract this by the one on the other side, which is the partial fx over partial y. Oh, sorry. This there should be multiplying everything by dy and multiply everything by dx. My bad. And then because of this, everything is multiplied by dx dy. You could just do it yourself. So it's this thing multiplied that by dx dy, and this is for a very small. This is for a very small contour, and for larger contours, you could just combine the things up, and so some things will cancel each other out. So what you would have is that this contour integral of f dr for any type of curve is going to be the same thing as the double integral of partial fy over partial x minus partial fx over partial y dx dy. Or you could denote this as just the a vector, and this guy to be at the k hat vector. And this thing here is what we call as the curl. So if you later just generalize this into a much more bigger, if you are doing this within 3 dimensions, it could be written as the integral of f vector dr vector to be equal to the double integral of the curl, which is written as this, the a vector. So what we have is that if we have a line integral, we could express this as the same contour, but instead we find the surface integral. And sometimes this is very useful, since sometimes doing it straight away from the line integral doesn't solve anything. So this is why sometimes we convert it into the curl. And so there are names for this. For 2-dimension, this is called as Green's theorem. But for 2-dimension, this is called as, no, sorry, for multi-dimension, this is called as Stokes theorem. So something that you might ask is, what is the direction of the A vector? Since you might have a negative value instead. And so this is the method that you would use. If you have a path here, the direction of the area will correspond to the right-hand rule. Same thing. Put your index finger in this direction, and then put your middle finger towards your surface. It could be any type of surface. So maybe it is straight away, something like this. You could do it straight away. And then what you would get is that the direction will go outwards, towards you. And this is your dA vector. And so you could do this for any type of surface. It could be very arbitrary, like a surface of a circle, or maybe it could be much more spherical. It will result in the same value. And so this curl here, the way that you could actually compute this curl is that the curl is defined to be the I hat of partial f z over partial y minus partial fy over partial z plus the j hat in the partial fx over the partial z minus the partial fz over partial x plus the k hat in the partial f y over the partial x minus the partial fx over the partial y. So this is the definition of the curl, and maybe this might seem to be a very long type of method for you to compute the curl, but later when we talk about matrices, you could actually do this in a much more faster manner. But anyways, this is the formula for the curl, and for any type of coordinate system, as long as it's orthogonal, there is a formula for this, in which I will also try to derive for you all. So in general, the df.dr is the gradient, sorry, the curl of your force. And so with this, what we could do is that the d.dr vector will be very small. So we'll just ignore that. So we'll just be doing df vector dot dr vector, the same thing as the curl. So if we are able to compute this, we already pretty much just solved this. Technically, this is times dA vector as well. So if we do the same method as before, we could express the df vector to be okay. So instead of opening this straight away, what we'll be doing is we'll just be taking the df.dr vector, right? But we'll just be expressing this straight away. So it's f1 of this guy, the dr vector, in which we have already known if we take the derivative with respect to t, it will be something like du1 over dt of h1, which corresponds to the scaling factor. So you would have this plus f2 of h2 du2 and f3 h3 du3, and this must equal to the gradient that we are trying to find, and the dA vector. And the dA vector will be, depending on your coordinate system, it's h2 h3 of du2 du3. And why is this? It's pretty much telling you that you just take a very small changes with respect to u2 and u3 with the scaling factors, and you're just taking the area. This is your small area. But this is only in your particular direction of E1. You need to do this for other sides. So like H1, H3, the du1 du3 for E2, and then for E3 it's H2 H3 du2 du3. Sorry, 1 and 2, and du1 and du2. E3. So for the front part here, because the the derivative of another derivative is very small, we'll just ignore it. So using the product rule, we'll get the df1 h1 du1 plus the df2 h2 du2 plus df3 h3 du3 must be equal to this entire thing. So from this thing here, because f1 h1 is like a scalar value, what we could express this is that because this is a differential form, we could extend it for every single coordinate system. So like du1 and du2 and du3. So we could just express everything out. So we'll just do it only for this guy first. df1 h1 could be denoted to be the df1 h1 over du1 times du1 plus another one here, it's the df2 h2 over du2 of du2, and then the df3 the h1 df1 h1 over du3 of du3. Now you could extend it for all of them, but here's something to note. du1 times du1. What I want to highlight here is that du1 times du1 must to be an area. We have already get rid of the idea of the area, and then now we are introducing it back. And the reason of this is very arbitrary, since the way that I try to differentiate this is technically not the correct way, but this is a very imaginative way. So it's like taking du1 multiplied by another du1, so it's like the same direction. It means that it doesn't have an area, which means that what will be left over is df1 h1 over du2 du1. And then here's the same thing for du3 of du3 du1. And then this will extend further for the other terms. Now, with this in mind, what I want to highlight is that the order also matters. It determines your direction. So u2 and du1 corresponds to a negative value, but u3 and u1 does not correspond to a negative value. So the way that you could correspond to this is that 1 to 3. If 1 goes to 2, it's positive. Same thing like this and this. But if you go it in the other way, it's negative. So this is why you would have the terms that is positive, negative, and so on. And so with these two facts, if you actually combine them together and try to guess what's the curl, you could have a very good guess of the curl to be the following. You could take the partial h3 f3 over, no, sorry, let's do it like this. So in the first direction, you are going to be dividing it by h2 and h3, which comes from this part here. And then you are be taking the, so this will be from your first part, which has the du2 and the du3, which is going to be corresponding to partial u2 of f3 h3 minus partial f2 h2 over partial u3. And then for the e2 direction, so you add this by the e2 direction, it's h1 and h3. It's going to be the 3 first and then the 1. f1 h1 minus f3 h3 over u1. And then for e3, it's h1 h2. It's going to be it's 3 1 2. So this is 2 u2. H2. This is u1. Subtract that by partial f1 h1 over partial u2. And this is the formula for the curl for any type of coordinate system. So we have finally discussed about the curl of an object. So So after the curl, we could now start to discuss about the divergence. And the way that we'll discuss about the divergence is by actually doing the integral of f dot ds. And so if we take the contour surface integral of f ds, we could just express this as something like a cube. And then you could express it for each of the sides. So we could do this straight away. So we could have fx in the d. So if we denote this to be xyz, this would be dx dy in the negative direction, and technically this is fz. So the negative fz dx dz, and then you would have the component in the fz dx dz, dx dy of the dz, but instead it will have a difference in x point y point z plus dz. So that's the difference, and then this would extend towards every single cardinal directions. So this could later be combined straight away because this is x point y point z anyways. This would be fz over partial z dot dz dx dy. And so this is something that you get for every single component. So it's simply written as fx over partial x plus fy over partial y plus fz over partial z of the dv, and then you take the triple integral, because technically in here there's double integral, and then you introduce a new integral here. So you have a triple integral of this surface, of this closed surface, to be this guy here, in which this is something which we'll call as the divergence of f. And so this thing here, this relation, is something which we call as the Gauss theorem. And this nabla dot f corresponds to the divergence. And so there are also formulas for you to solve for the divergence in other coordinate systems. So the way that you could do this is by using the same logic. If you take like the very small change of f dot dA, this would correspond to the gradient of f dv. So we could just solve for the front part first. This is the d of fx in dy dz plus the fy in the dx dz, and then lastly fz in the dx dy directions. This would be the nabla f dv. So if you do the, this would be u2 and u3. So f1, f2 of u1, u3, and then f3 of du1, du2. And then each of these are multiplied by the h2 and h3 because they are scaling factors. h1, h3, and h1, h2. So what you would end up with is the df1, h2, h3 of du3, du2, du3, plus the df2, h1, h3 of du1, du3, plus the d of f3, h1, h2 of du1, du2. And so if you divide it by the dv, or the dv here is h1, h2, h3, du1, du2, and du3, what ends up happening is this will be the f1, h2, h3 over du1 plus the f2, h2, df2, h2, h3 over du2 plus df3, h1, h2, this is h1, over du3. And everything is divided by 1 over h1, h2, h3. And this is the formula for the divergence in other coordinate systems here. So after all of this discussion, we have talked about this symbol, but we haven't really discussed about what this is. So this is what we call as the differential operator, del. And it is normally written as partial over partial x in the I hat direction, partial over partial y in the j hat direction, and partial over partial z in the k hat direction. So this is a very useful notation because you could do cross product, you could do dot product, you could do the gradient or like vector multiplication straight away with a scalar to get your gradient, divergence, and curl all together. And you could also express this in other coordinate systems. And it works pretty similarly to the one we did for the gradient vector. So it would be just E1 over H1. It's EI over HI. Sorry. It's EI over HI partial over partial UI. You just take the sum of all of this. It's that simple. But here's something that I want you to remember, is that you couldn't really use this straight away when you're applying this for divergence or curl. You would need to use the formulas that we have already given you because this is an operator. It is technically not really multiplication, but luckily when we convert it in terms of this, in terms of the Cartesian coordinate system, it turns out that it has a very useful identity when we talk about the curl as well as the divergence. So after we have talked about the del operator, we could now start to discuss about higher order derivatives. And so there are 5 of these. So if you have a scalar function, you could take the gradient and it will result into a vector. And so you could do 2 things. You could take the dot product or you could take the cross product. And same thing for the force fields. You could do the dot product, which results to a scalar, meaning that you would take the gradient, or you could have it to be a cross product and take it with another dot product or take it with another cross product. So here are some properties that could be extracted from each of these. First, I want to discuss about the curl of a gradient. And so the way that you could actually symbolize this is if you take the double integral of the curl over the gradient dA, it will be the same thing as the closed integral of the gradient of phi dr. And something to remember is that the line integral or the contour integral of a gradient is always equals to 0. It is conservative, meaning that this starting is actually equal to 0. And same logic applies here. You can take the triple integral of the divergence of curl, and what you would gain is something like this, the closed integral of curl. Sorry, this is dv, this is dA. And this actually results in 0. And so there are also other ways for you to interpret this. For this one, you could actually express it as if you have your surface ready. So this is a closed surface. So if this is like a sphere, you could just bisect it into 2, and then you would have the same boundary for the loop integral f dr. And so you're doing it for the left side as well as the right side, and later they will both cancel each other out. That's why you would get the 0. And so these are the 2 interesting facts about higher order derivatives. Another one is the divergence of the gradient, and this is called as the Laplacian. And there's something unique about the Laplacian, is that this function could be rewritten as partial squared of phi. Sorry, nabla squared of phi. And the Laplacian, if this equals to 0, is something which we call as the Laplace equation. And the solution of phi is something which you call as a harmonic function. Same thing that we discovered when we talked about analytic functions. It turns out that for an analytic function, the real part as well as the imaginary part both must be a harmonic function. So what about the other 2? This one here is something we don't really discuss, but this one, the curl of a curl, you could just expand it by taking the all of the nablas, and what you would obtain is this would be the same thing as the gradient of the divergence. Subtract this by the Laplacian of the vector field. And this is very useful when you're doing classical electromagnetism, in which we'll be talking a little bit about throughout this entire discussion after this. So there are lots of useful things that you could use when you're doing vector calculus. No, sorry. There are lots of useful tools from vector calculus that you could apply for physics. One of them is obviously the Maxwell's equation. So this is the Maxwell's equation. This is rho over epsilon 0. This is 0. This is negative partial b over partial t. And this would equal to mu 0j plus mu 0 epsilon 0 partial e over partial t. So these four Maxwell's equation governs the entire electromagnetism. And then normally this is written as the integral form, but you can also write this as the differential form. And it is pretty useful if you know about the electric field. You could figure out your rho, your magnetic field, your currents. Everything is within here. But if you are talking about, but sometimes it is also useful to use the integral form. Sometimes for things like the total charge or like the total density, the total current, you normally use the integral form. And so it is pretty interchangeable, and also something useful when you use the differential form is that the differential form gives you a very big clue when you talk about electromagnetic wave. So if you think about this equation, which is the nabla over nabla dot E minus the nabla squared of E, and then we assume that this is within vacuum, so rho equals to 0, as well as j equals to 0, what we see is that this is nabla plus negative partial b over partial t is the same thing as the negative nabla squared of E. Now, with this, if we take the nabla clause, if we take the curl of this changing magnetic field, you could just swap them out because this is continuous. So we would have the negative partial over partial t of the nabla cross b, which is the mu 0j of mu 0 epsilon 0 partial e over partial t, which will be this. And this will later simplify much more further into a wave equation, forming something like this. So this wave equation tells you that the speed of light is 1 over square root of mu 0 epsilon 0. This is one thing that you discover when you talk about electromagnetism, thanks to vector calculus. Another very useful fact, in which this is something that I just learned, is that if you take the second and the third Maxwell's equation, nabla dot b as well as nabla cross e plus partial b over partial t, they both equals to 0, meaning you get a certain information out of this. If you remember that the divergence of a curl is 0, so we will just denote a very random a to be our vector, as long as it is the curl of your a, which is the magnetic field. It pretty much describes the magnetic field. And same thing if you talk about this part here, and it is a little bit much more hidden. But if you substitute b to be the nabla cross a, what you would get is the nabla cross E plus the partial A over partial T. And this is normally denoted as the negative of the gradient of a scalar function or a scalar field. And this is because this thing here, the curl of a gradient is always 0. So you would get something like this as well. And with these two informations, you could gain informations about the electric field as well as the magnetic field. And these two relations actually govern all of electromagnetism. It's like another way for you to view electromagnetism. Instead of electromagnetism as well as the magnetic field, you could just express it in terms of two different potentials. The vector potential as well as the scalar potential. But I won't fully discuss all of this crazy physics with it here because this is something that I just learned. So if you want more discussions about this, please leave it in the comment for me to discuss much more further. But anyways, that's all for today's video on vector calculus, in which we studied starting from vector analysis towards the way that you do differential vector calculus, and then we did integral vector calculus. And so that's all for today's video, and make sure to like and subscribe, and also please share this to your friends who really needs to understand the mathematics behind physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.